Okay, welcome back everyone. In this segment, we're going to start talking about projectiles and how they relate to our discussion of two-dimensional motion. So basically what we're trying to determine in this video is how can we describe the curved path followed by a projectile. Okay, so first of all, here's the trajectory of a projectile. And thanks to Physics Classroom for some of these diagrams. But this projectile is launched at an angle to the horizontal and rises upward to a peak before falling back down. And the definition of a projectile is any object that is moving only under the influence of gravity. So it's in the air. We're not going to worry about air resistance yet. It's not in space, but it's just moving, and gravity is really the only force. So there's no rockets or air resistance or anything to kind of affect its motion. Okay? So this has an acceleration which is negative 9.8 for the entire time. Now, what happens is that the velocities are actually going to change during its trajectory. And Vy is going to change because we know that Vy final is equal to Vy initial plus gravity times time. That's just our velocity equation. So that means that Vy is going to be decreasing as time goes on because g is negative 9.8. And what we'll typically do with projectiles is we will take the velocity and split it up into pieces. So if I have a velocity v right here and an angle theta and Vx and Vy, then I will typically write Vx is equal to V cosine theta and Vy is equal to V sine theta. Okay, so let's think about what the position of a projectile will look like. And we're going to start with the x versus t graph. And because there's no other forces, basically a projectile will maintain a constant x velocity. So that means that x versus t will be fairly constant, or delta x will be equal to Vx naught times t. So whatever velocity it starts with is what it will keep. Now delta y, on the other hand, we're going to take our equation for delta y from 1D motion and we'll just plug in for gravity for the acceleration. And since that g is negative 9.8, we're going to have a downward opening parabola. Okay? Now one thing that you might notice is that if you then take this time t as delta x over Vx initial, and if you plug it in for t in this equation, you're going to essentially get a quadratic. So delta y is going to be still proportional to x squared, and we get another parabola. So we'll talk a little bit about the details of this a bit later on, but let's look at velocity graphs. Now we said previously that delta x was equal to Vx naught times t. So that suggests that Vx final is equal to Vx naught. There's no acceleration, so it's just going to start at some constant value of Vx naught, and I'll just stay there. Okay, Vy, on the other hand, will have a starting value of Vy naught, but Vy is going to be equal to Vy naught plus gt. But remember, again, g is negative 9.8. So this is going to decrease with a slope of negative 9.8. And we should also note that this point right here, this is where v is equal to 0, Vy is equal to 0 rather, which is at the top of the path. Okay, top of the path. Now it's a misconception that the acceleration is 0 at the top of the path, and you can see clearly that we still have a negative slope here, so the acceleration is not 0. They like to write AP questions to trick you about that. And speaking of acceleration, what would it look like? Well, AX is going to be 0 because VX is constant. Okay, so the slope of that, or AX, would be 0. And AY is going to be stuck here at negative 9.8, which is equal to G. Okay. So, one thing to remember when we're doing projectile problems is that you want to resolve the initial velocity into components. So again, if you have theta and v initial, you can have vx initial is v initial cosine theta, and vy initial is v initial sine theta. So let's see how to solve an example problem. A soccer player kicks a ball at 15 meters per second at an angle of 35 degrees above the horizontal. It's over level ground. How far horizontally will the ball travel until it strikes the ground? Okay, so there's basically 3 different types of projectile problems. And the first is what we call a horizontal launch. And horizontal launch is, for example, a marble rolls off a table. So that means that basically Vx is there, but Vy initial is 0. Well, that's not what this problem is. This is the second type of projectile problem. This is a delta y equals 0 problem, where something starts on the ground, goes up, comes down, and lands on the ground, and since y final is equal to y initial, the difference between those is 0. Okay, there's the ground for the horizontal launch. And then the third is what I like to call just uneven level. So, for example, something starts on the ground and ends at the top of a cliff. It could be like horizontal launch, but backwards. Okay, now which one do we have here with the soccer player? Well, we've got the second type. And the advice that I give you for all projectile problems is to write the equations for delta x equals ... and delta y equals. And this is going to take you a long way in solving pretty much all projectile problems. Okay, so let's think about that. Okay, we have delta x is equal to vx naught times t. So that's just our distance equation. Remember, there's no acceleration in the x direction. So delta x is equal to, well, hold on a second. Let's break this down. We want to take our v initial, which is 15, and angle of 35 degrees, and find vx initial and vy initial. Okay, so vx initial is actually going to be 15 cosine 35 degrees, but we have a problem. We don't know what the time is. Okay, so we're left with 2 variables, which is why we have the second equation for delta y. So delta y is going to be equal to vy initial times t plus 1/2 gt squared, and delta y is 0. Okay, so we can plug that in for delta y, and vy initial is going to be this guy here, which is going to be 15 sine of 35 degrees times t minus 4.9 t squared. So I'm using the fact that g is negative 9.8. Okay, now you might notice that this t and that t are going to cancel out, which allows me to avoid a quadratic and get a time of 1.76 seconds, or, and this is important, I kind of crossed it out, but the time could also be 0. And that corresponds to right here, 0 and then 1.76. So that works out. And now that we have the time, we can bring it back to here, and 15 cosine of 35 is like 12.3 meters per second, and 1.76 seconds is going to give us about 21.6 meters for delta x. And that was what we wanted to find. Okay, let's do one more example and then we'll move on. So in this example, we have a cannon fired at a 15-degree angle above the horizontal from the top of a 120-meter high cliff. How long will it take the cannonball to strike the plane below the cliff. Now, I'm not sure if this is a math error, but I think I meant to write plane, P-L-A-I-N. It could also be a plane, namely the XY plane, but I probably just misspelled it. And how far from the base of the cliff will it strike? Okay, so here's our picture. There's the cliff, there's the plane. I'll spell it this way. And something is being launched from 15 degrees, so it's going to go up slightly and come down. And this means that we have the third type of projectile problem, the uneven launch. And the only thing that we can do with an uneven launch problem is just set up our two equations for delta x and for delta y. Okay, so I'm going to assume that you're comfortable with finding Vx initial, because this is Vxo times t. Okay, so that means that delta x is going to be equal to, let's see here. Oh, I apologize. Let's also say that V 38 meters per second. Okay? Otherwise, things get kind of funky. So delta x is going to be 38 cosine of 15 times t. And just like the last problem, we have two variables and two unknowns. So we need to plug in for delta y. So this cliff is 120 meters tall, and delta y is Vy initial t plus 1/2 gt squared. We can plug in what we know. Now we have to think carefully about this. If the cannonball starts on top of the cliff and ends at the ground, what is its delta y? Well, if we say that upwards is positive, it has decreased 120. So negative 120 is its delta y. Vy initial is still going to be 38 sine of 15 degrees, and we have a t. Oh. And then we also have minus 4.9 t squared. And what you're going to notice is that now we have a quadratic. Okay? And this quadratic has two answers. It has a positive answer of about 6.05 seconds and has a negative answer that I didn't calculate. Okay? Now what does that negative answer signify? Well, first of all, the positive answer is the correct one for the time, and that's what we'll plug in here in a moment. But the negative answer means something. And basically, if we take this parabola and work it backwards to see like where it came from, that would be a negative amount of time, because t equals 0 is from the launch on top of the cliff. So there is usually significance in these things. Okay. Now, finally, what we would do is we would solve for delta x, which is what we want. How far from the base of the cliff will it strike? And that's going to be 38 cosine of 15 degrees times the time, which is about 6.05 seconds. Okay? And that's going to get us approximately 220 meters for our answer. So the big takeaway here is that I'm still applying two equations because I know that I have two unknowns. Okay, so next time we're going to look at some more theory in projectiles, and we're going to come up with some equations for how far a projectile travels and what its maximum height is.